Hello, in this video we are going to attempt to solve the following non-linear ordinary differential equation: 2y double prime equal to 3y squared, subject to the initial conditions which state that at x equals 0, y is equal to 1 and y prime is equal to 1. Now, y prime is equal to dy by dx and y double prime is equal to d squared y by dx squared. Now, to solve this equation, we're actually going to write down the initial equation again. So we've got 2y double prime equals 3y squared, and we'll call that equation 1. Now, to solve this equation, the only option available to us is to use a substitution. So we let u equal dy by dx, and this means that let me just make a little bit more room. So this means that d squared y by dx squared is equal to du by dx. Now, we could substitute du by dx straight back into y double prime, but the problem is there we end up with a u, an x, and a y on the right hand side. And that's a problem because you can't have three variables of any type in an ordinary differential equation. You can only have the maximum of two in order to solve it, as you were probably aware. So what we do is we use the chain rule. And I'll write this down. We use the chain rule to expand this second derivative. D squared y by dx squared equals du by dx. So in actual fact, what this becomes is d squared y by dx squared equal to du over something times something over dx. Now, because we're dealing with the dependent variable, the independent variable y, then we choose this to be dy there in the numerator and dy there in the denominator. So if you remember, what I've just said is, oh yes, here we are. I've just said that we're letting dy by dx equals u. So we substitute u in for dy by dx here. So what we have is du by dy times u, and this is normally more conventionally written as, and I'll write it out again, so we've got d squared y by dx squared equal to u du by dy. So we can now substitute u du by dy, this term here, into equation 1, so that we get 2u du by dy equal to 3y squared. And we're going to write that down. So equation 1 can be written as 2u du by dy equal to 3y squared. Okay, so now we can integrate this very easily. The 2 and the 3 are just constants, so they can be written outside the integral signs. So we get 2 times the integral of u du, and that's equal to 3 times the integral of y squared dy. Right, so we've effectively separated variables and we're integrating with respect to y or dy. So this integrates very easily to 2u squared over 2, and that's equal to 3y cubed over 3 plus a constant of integration, c1. Now, as you can see, the constants here, that the 2 cancels with the 2 and the 3 cancels with the 3, so that we're left with u squared equals y cubed plus c1. But as we've just defined above, let me just go up here, dy by dx is equal to u. So we write u equals dy by dx. So we call this equation, what equation are we calling it? So we call that equation 2. Equation 2. So equation 2 becomes, we have to go on to a new page now, becomes dy by dx all squared equal to y cubed plus c1. Now, we're not finished because we want to find a solution for y in terms of x. But before we do that, we have to substitute in the initial conditions. So the initial conditions state that at x equals 0, y equals 1, and y prime equals dy by dx equals 1 as well. So therefore we have 1 squared equals 1 cubed plus c1, and as you can see, this implies that c1 equals 0. You just subtract 1 from both sides, c1 is 0. Therefore, I think we'll call this equation equation 3. So we'll just call that equation 3. So equation 3 becomes right, let's just scroll up a little bit. Dy by dx squared equals y cubed. Now, this looks rather difficult to integrate because we've got a nonlinear derivative effectively on the left-hand side and another nonlinear term on the right-hand side. But lo and behold, we can simplify this before we do anything else. And we can do that by taking the square root. Now I'm just going to take the positive square root of both sides. You could take the negative square root of both sides, but we'll just stick with taking the positive square root. It's a lot simpler for getting, for the purposes of getting to a solution. So we've got dy by dx equal to y cubed all to the power of half. That's, so we've square rooted both sides to get this, and that on the right hand side simply becomes y to the power 3 over 2. Now this equation is actually separable for the purposes of solving it further. So what we do is we divide both sides by y to the power 3 over 2 and multiply both sides by dx. And we stick in integral signs as well. So we've got dy over y to the 3 over 2. Don't forget the integral signs. And that's equal to the integral of dx. Now, I'm sure if you're doing this level of mathematics, solving nonlinear differential equations, you know that to integrate the left-hand side, you simply basically bring this y to the power 3 over 2 to the top into the numerator. So we get y, or the integral of y to the power minus 3 over 2 dy, and that's equal to the integral of x. So we can now integrate this, and what we obtain is y to the minus a half all divided by minus a half, and that's equal to x. In fact, actually, I made a mistake there because that should be dx, shouldn't it? Yeah. So that's dx. And so the dx integrates to give x plus, I think this is going to be a C2, isn't it? A constant, another constant of integration, which we're calling C2. Yeah, because we had C1 there. Okay. Let me just scroll down. So we've got this expression, but we want to simplify it. So anything divided by a half is 2. And of course, you divide by minus a half, you've got minus 2 on top. And of course, the y to the power minus a half just becomes effectively 1 over y to the half there. So that you just go back here, all of this on the left hand side simply becomes minus 2 over y to the half here, and that's equal to x plus c1. Now we have to use the initial conditions again, because when, let's just write this down again, when x equals 0, y equals 1. So we've got minus 2 over 1 to the half equals x plus c1. In fact, actually, it's not x plus c1, is it? It's 0 plus c1. There we are. I wish I didn't make these mistakes, but nevertheless, I've seen it. And by the way, where I've got 1 to the power a half, that is a square root of 1, which can be written as plus or minus 1, but I'm taking the positive square root. You can try it with a negative square root, like I said before, earlier on in this video. But we shall just stick with the positive square root, so that what we're left with is minus 2 equals C1, or C1 equals minus 2, basically same thing. So now we go back to our equation. We need to label that equation, but I've forgotten what labels I had before. So that was equation 3, and we'll call this equation 4. Thus, equation 4 can now be written as minus 2 over the square root of y minus 2 over y to the power half equals x minus 2. Is that right? Yeah. And in actual fact, we can rewrite that as y to the power half equals 2 over 2 minus x. To get the actual solution for y, we square both sides, and we get y equals 4 over 2 minus x all squared, and that's to be rewritten. I'm rewriting it like this for a reason, because we're going to check that we've got the right solution. So normally you'd leave it like the solution like that, but I'm writing the solution like that as well, because we're going to show that that is the correct solution by performing a check, as it were. So let's do that. We know that y is equal to 4 times 2 minus x all to the power minus 2. This means that y prime is equal to, and presumably you know how to differentiate this, you bring the minus 2 down in front of the 4, and you get minus 8 times 2 minus x, and then you differentiate the 2 minus x inside the bracket to get minus 1, and that simplifies to y prime equals 8 2 minus x, and actually I've missed something out, haven't I? That becomes a minus 3 up there, and that becomes a minus 3. So y prime is equal to 8 times 2 minus x all to the power minus 3. So differentiating again for y double prime, we get minus 3 times 8, which is minus 24, times 2 minus x all to the power minus 4 times the derivative of whatever is in the bracket, 2 minus x. So the derivative of that is minus 1, and we find that y double prime is equal to 24, 2 minus x to the power minus 4. Let me double check that that's right. That looks okay. Now I'm going to rewrite this y double prime as 24 over 2 minus x all to the power 4. Now, if you remember, in equation 1, is it up here? Yeah. So in equation 1, we had 2y double prime equals 3y squared. Well, we want to prove that the left-hand side, 2y double prime, is equal to 3y squared. So we'll just consider the 2y double prime bit. So if we go down, and just scroll up a little bit, then we find that 2y double prime is equal to 2 times 24 over 2 minus x to the power 24. Now, this can be written as, well, 24 is divisible by 3 to give 8. 8 3s is 24. So we can take a 3 outside this, and we've got the 2 there times 8. So just as a check, 3 times 8, 3 8s is 24, and that 2 is that 2 on the outside. So let's just get rid of those little underline marks and continue to write the bottom bit. We'll write this here, 2 minus x to the power 4. Okay, well, how does this help us? Well, we'll just write down 2y double prime again, and that's equal to 3 times, well, we've got 2 times 2 cubed there over 2 minus x to the 4. I'm sure you will agree with me that 2 cubed there is equal to 8, and there's our other 2. This is exactly the same as saying 3 times 2 to the 4 over 2 minus x all to the power 4. Right, how does this help us? Well, let's write this as 3 times 2 squared over 2 minus x all squared, and then we'll write a bigger box there with squares outside it. Right, now let's just have a look at what y was. So we had for y 4 over 2 minus x squared. Just go there. So we'll just rewrite this in more familiar terms. 3 times, in brackets, 4 over 2 minus x all squared. Right. Okay. But y equals 4 over 2 minus x all squared. So we're nearly there. Just make that so that you can read it. 2y double prime is equal to 3, and then in the brackets we just replace that 4 over 2 minus x all squared with y, and on the outside we've got that squared term, and that is equal to 3y squared as required. So 2y double prime is equal to 3y squared. That has got us right back to the original equation in equation 1. 2y double prime equals 3y squared. So we can pretty much guarantee that y equals 4 over 2 minus x all squared is a solution, at least one solution, to that original ordinary nonlinear ordinary differential equation. So I hope you found that interesting and helpful, and until next time I shall bid you farewell, and bye for now.